In this video, we look at two distributions, the geometric distribution and the binomial distribution. So we have seen the normal distribution. This is what we use most often in Introduction to Statistics. But I want to make you aware of two additional distributions and show you how we can use StatCrunch to find the values corresponding with these distributions. The first distribution we're going to look at is the geometric distribution. The geometric distribution is used to describe how many trials it takes to observe a success. Geometric distribution calculations are used by gamblers, insurance companies, lotteries, and other scenarios with repeated trials with the same chance or probability of success. Let's consider the card game Hearts. It's a trick-taking evasion game where the player wants to minimize points to win. Some of you might have played Hearts on your cell phone. It's a common solitaire game, or you might have played with family and friends. Heart cards count as penalty points in the game. In a standard deck of cards, each suit is a quarter or 0.25 of the deck. We can calculate the probability of drawing a heart card as P equals 0.25, and the probability of drawing a diamond, a club, or a spade card as what we call Q, the opposite of P, or the complement of P. So 1 minus P, or 1 minus 0.25, is 0.75. So 25% or 0.25 of the time when you're randomly selecting playing cards, you'll get a heart. The other 75% or 0.75 of the time, you'll get a diamond, club, or spade. We are going to consider drawing a heart card a success. We will assume that the player is drawing from a deck of cards at random and that each draw is independent. The probability that the first player draws a heart card is going to be 0.25. So now let's think about, well, what if the first player does not draw a heart card? Then we can calculate the probability that the second player is the first person to draw a heart card. So here, and I've highlighted it in yellow to be easier for you to see, we can say the probability the first won't, meaning the first won't draw a heart, but the second player will, is going to be 0.75 times 0.35. I think that is a typo and should be 0.25. So I apologize, it's a typo. It should say 0.75 times 0.25. I will fix that for future students. So the probability that the first is not going to draw the heart, that's a 0.75 chance, and then the second does is 0.25. And so you can check if you multiply, you get 0.1875. So we say the probability that the first or second player draws a heart card is 0.25 plus 0.1875. So we're starting with the 0.25 because that's the chance that the first player draws a heart card, 1 out of 4. And then we add up the probability that the second draws a heart card if the first doesn't. So when we add those up, we get 0.4375. All right, similarly, the probability that the third player is the first to draw a heart card is the probability the first won't, the second won't, and the third will. And that is 0.75 times 0.75 times 0.25. And the 0.75s are the instances where we're assuming the first won't draw a heart. That happens 75% of the time. The second player won't draw a heart. That happens 75% of the time. And then the 0.25 is that the third does draw a heart. So we are able to multiply these because we're assuming each player drawing cards is independent. It's not related to what the last player is drawing. And so here we get, when we multiply 0.140625. All right, so if the first success is on the nth player, then we say there are n minus 1 failures drawing a heart card and 1 success, which corresponds to the probability 0.75 to the n minus 1 up in the exponent, because that's how many failures there were, times 0.25. So in my scenario, we must be assuming the deck is restocked every time, or that it stays always 3/4 not hearts and 1/4 heart. If you actually do the math, if we assume a little more complicated scenario where the hearts are coming and going and it's changing the ratios in the deck, then the math would be a little bit different. So we're assuming here the deck gets restocked every time. In general, we could say the formula is 1 minus the probability of the event happening raised to the n minus 1 times p, the probability of the event happening. All right, we want to use StatCrunch to create a graph of this geometric distribution. So In a blank spreadsheet, we're going to go open StatCrunch and click Stat Calculators Geometric, and we're going to do our calculations by the number of trials. And so let's head over to StatCrunch and do that calculation. So here I've got StatCrunch open in my browser. I'm just going to open a blank StatCrunch. And then I'm going to go Stat Calculators. This is where we've worked with the normal calculator before, but I'm going to come over to the geometric calculator and choose number of trials. So we want to verify our calculation for the probability that the first or the second player draws a heart card. So the probability of hearts is 0.25, so I'm going to change my P here to be 0.25. And then we're looking at the first or the second player, so this is the probability that X is less than or equal to 2. If we wanted just the second player draws hearts, we would come down here and choose equals. And if we hit compute, we get 0.4375, which matches what we added up. If we wanted just to check our calculation that the second player gets hearts, we can come down and choose equals. And there is that 0.1875 that we calculated. Notice that corresponds with the red bar in the geometric distribution. We can adjust this back to less than or equal to, and we see the two bars shaded in red correspond with the first player getting hearts or the second player getting hearts when they're drawing cards. And again, we're assuming this is like a fully stocked deck, or the proportion of hearts and the other cards stay the same, 0.75 and 0.25. In reality, if you're thinking about pulling cards out of a deck and not replacing, then the calculations get more complicated because you have to take out whatever card was drawn first. All right, now we want to do a calculation for what if the first player doesn't draw hearts, the second player doesn't draw hearts, but the third player does draw hearts. So let's head back to our calculations. So if we're calculating the third player as the first to draw hearts cards, we saw that would be 0.75 times 0.75 times 0.25, or work out to be 0.140625. So if we want to figure out the probability that the first, second, or third player draws a heart card, we add up 0.4375 plus 0.140625 and get 0.578125, or right around 57 to 58% chance that one of those first three players draws a heart card. So let's head into StatCrunch to verify that calculation. So I'm going to keep my probability at 0.25, but calculate the probability that X is less than or equal to 3. And so that's shading in our graph the red bar for the first player drawing a heart, the second player drawing a heart, and the third player drawing a heart. And that works out to be just what we got, 0.578125. If you want to verify our calculation that just the third player draws hearts, you can change your inequality to be an equal sign. And there is that calculation 0.140625 that we calculated, and the third bar is highlighted. Notice the geometric distribution is a discrete distribution. It's not a smooth curve like the normal curve. We are just having counts for discrete events like the first player draws a heart, the second player draws a heart, the third player draws a heart. Our next example takes a look at the binomial distribution. So the binomial distribution is used to describe the number of successes in a fixed number of trials. This is different from the geometric distribution, which describes the number of trials we must wait until we observe a success. Like the geometric distribution, the binomial distribution is used by gamblers, insurance companies, lotteries, and in other scenarios with repeated trials with the same probability of success. So we are going to consider the game Hearts, where the probability of drawing a heart card is 25%, or P equals 0.25, and the probability of drawing a diamond, club, or spade is, we call it Q, or 1 minus P, or 0.75. And we can verify P and Q always add back up to 1 or 100%. In a game with 4 players, each player is dealt N equals 13 cards at random, and then we assume independent from the other players. If there's some relationship in how the cards are dealt, then we couldn't do any of these calculations. So we want to figure out what's the probability of a player being dealt at most 4 hearts cards and a hand of size N equals 13 cards. So we are going to look at the binomial calculator. So we will go into StatCrunch, go to Stat Calculators, and then open up the binomial calculator. So I'm going to head back to my StatCrunch window. I can just exit out of my geometric calculator, and it'll be up here in my results if I want to come back to it. And then I'm going to go to Stat Calculators and choose binomial right up here with the B's. So you can see the binomial distribution is shaped kind of similar to the normal distribution, but it's discrete. I'll go ahead and make mine a bit bigger for you to see. And so we need to adjust our settings. We're assuming there's 13 cards to each of these 4 players. So we're going to say n equals 13. And then we're going to say the probability of hearts is 0.25. And then we want to verify or calculate the probability that a player is dealt at most 4 hearts cards. So that's the probability that x is less than or equal to 4, where we're saying x is a heart card. And if we hit compute, StatCrunch draws us the geometric distribution. Now notice, in this scenario, our geometric distribution isn't quite so symmetric anymore. It's got a little bit of a tail off to the right. So depending on how big your sample is and what probability you're working with, the geometric distribution can be skewed or it can look symmetric. It looked symmetric when we did the default. So if I go Stat Calculators, binomial, see here it looks, the binomial distribution looks symmetric when the probability is 0.5. But when we switch probabilities, we got a skew here. All right, so this should match the screenshot for the binomial calculator that you have here in your PDF or in your activity packet. So we see the calculation is 0.7939619. So almost 80% of the time, if you're dealt 13 cards at random, you're going to have less than or equal to 4 hearts cards. Question A asks us to use the binomial calculator in StatCrunch to find the probability the player is dealt no heart cards. So that's the probability that x is 0. So notice, right now we're saying x is less than or equal to 0. This would be okay and give us the same result as saying x equals 0 because there's no negative possibilities. But we can actually click our inequalities and change it to the equality symbol. And so they say the probability x is 0, meaning no hearts cards, is 0.02375,726. I'm going to round that to 0.0238. And so you can see over here, the probability x equals 0, no heart cards, is right around 2%, 0.0238 rounded. Now in part B, we want to figure out the probability that a player is dealt all heart cards. So we're going to head back to our StatCrunch and change 0 to be 13 and go ahead and hit compute. So the chance of all heart cards is really unusual. And so we see it is almost 0. We can call it 0.000001, or you could just say close to 0. So you'd be really, really surprised if you're playing a card game and you get 13 cards and they're all hearts. That means nobody else got any hearts. You got all the hearts. So here's a note about the formula for the binomial distribution. If you have k successes, that's how many times in this case you'd expect the hearts cards to come up. You get this formula with the k's in it, where the numbers with the exclamation points are called factorials. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. So you can see when you do a factorial calculation, you are multiplying the number times everything smaller than it. 1 factorial is defined as 1, and 0 factorial is also defined as 1. We are going to rely on StatCrunch to calculate the formula for us in Math 110. We are not going to do many problems with the geometric and binomial distributions, but I wanted you to see an example of how discrete distributions look and to see that they're used for calculations if you're thinking about gambling or if you're thinking about insurance companies and the chances of things like car accidents or fires happening, how the lottery works, and any other scenarios where you've got repeated trials with the same probability. The focus of most of our class in this chapter is on the normal distribution.